So hi, welcome everyone to this Precision Systems Teatime Webinar series. Today with us there is Saphia Matthew, who is a PhD candidate at the University of Strathclyde, and she is going to talk about her work, which is microfluidic manufacture for morphology control of silk fibroin nanoassemblies. So before starting to the presentation, I would like to let you know about your Europe team. There is Richard, Suha, and Ed are based in the UK. There is Jürgen and Martin are based in Germany, and myself, I am located in France. Please feel free to reach us out if you would like to know more about our technology. Thank you very much, and welcome again. Over to you, Saphia.
Hi everyone, today I'll be talking about my work in the SEEP lab exploring the morphology control of silk fibre nanoassemblies in microfluidic and semi-batch mixing regimes. We are using the silk fibre and biopolymer obtained through reverse engineering of Bombyx mori silkworm cocoons, as this material has clinically relevant properties and is well studied. The fibre molecules in the core of the spun silk fibre have a silk 2 structure, which is characterised by a high beta sheet crystallinity. Aqueous silk fibrin with a silk quantum structure and a low beta sheet content is then obtained through reverse engineering. Nanoprecipitation of aqueous silk fibrin by desolvation using water-miscible polar organic solvents such as isopropanol has been used since the 1990s to obtain beta sheet enriched particles. These are suited to drug delivery of cytotoxic, poorly absorbed drugs such as doxorubicin due to their submicron size and their net negative surface charge. The mixing time is a key process factor dictating the outcome of silk nanoprecipitation. In semi-batch format, the impact of decreasing the mixing time has been investigated in a semi-automated system with a syringe pump equipped with a horizontal needle for flow rate and feed height control. The mixing time decreased as the stirring rate increased and caused a reduction in the nanoparticle size and nanoparticle yield. SEM confirms spherical morphologies for nanoparticles produced at 200 and 400 RPM stirring rates. One solution for high throughput scalable manufacture has been the use of continuous technology, such as a staggered herringbone micromixer, which provides a high mixing efficiency during silk nanoprecipitation in isopropanol and acetone antisolvents. The nanoparticle physical chemical properties have demonstrated a dependence on the antisolvent properties, the total flow rate, and the flow rate ratio of the aqueous and antisolvent phases. The optimal conditions of a flow rate ratio of 5:1 IPA to silk precursor and a total flow rate of 1 mol per minute were then used in further work to analyse the impact of the silk precursor molecular weight by varying the sericin degumming time of the silk cocoons. However, further progress is needed for the manufacture of non-spherical particles by nanoprecipitation and for a better understanding of the silk self-assembly mechanism in the semi-batch and microfluidic formats. The aim of this project was to control the morphology of silk self-assembly using antisolvent-induced nanoprecipitation in semi-batch and microfluidic formats. We designed a closed, semi-automated system for these semi-batch formats to reduce the variability in operating parameters and use the staggered herringbone micromixer for the microfluidic format. The flow and mixing properties were characterised for both formats, and the stirring rate and the feed addition height of the semi-batch system was optimised. The self-assembly of silk fibrin under shear is a property utilised in the natural world during spinning of the silk fibre. To control the nanoassembly morphology, we utilise shear-induced nucleation of silk fibrin under flow in both the semi-batch bulk mixing and the micro-mixing conditions. We hypothesised that shear-induced nucleation and assembly could occur at flow rates where the critical shear rate was exceeded. The alignment of silk molecules and micelles under flow could result in assemblies with rod-like and fibre-like morphologies. Consequently, we use the optimized systems to vary process factors which control shear, mixing time, and supersaturation. The nanoprecipitation workflow begins with reverse engineering of the Bombyx mori silkworm cocoons. Briefly, the degumming process removes the sericin protein coat on the cocoon, and then the silk is then dissolved in lithium bromide, aqueous lithium bromide. Lithium bromide salts are then removed using dialysis, and the silk is further purified by centrifugation. The formulation is run by mixing the diluted silk precursor and the antisolvent in the desired format, and the nanoparticles formed are purified from the organic solvent by centrifugation. Finally, the structural and physical chemical properties of the purified particles are analysed. In this study, key processing parameters were set at levels which resulted in optimal nanoparticle physical chemical properties as determined in previous work in both the semi-batch and microfluidic formats. The mixing process was characterised for both the micro and the bulk mixing conditions. In semi-batch formats, we use the dual indicator system for mixing time method to determine the bulk mixing time, and found that increasing the stirring rate and the feed height reduced the mixing times, which were on the order of seconds. In the staggered herringbone micromixer, we estimated the micromixing time by first using the hydraulic diameter of the microchannel to approximate the rectangular geometry. We then calculated the Peclet and Reynolds numbers and found that the mixing time on the order of milliseconds decreased as the flow rate was raised. As the micromixing time was lower than the residence time, complete mixing was estimated for all flow rates. We then characterised the flow properties of both formats. We estimated the maximum shear in the micromixer and in the feed needle of the semi-batch format using the wall shear rates. In semi-batch format, the critical shear rate for the 0.5 to 3% silk, which is roughly about 350 per second, was surpassed at flow rates above 0.017 mil per minute, and in microfluidic format at flow rates above 0.001 mils per minute. We confirmed that shear-induced nucleation could occur at flow rates above 0.017 mils per minute using FTIR, which showed that increasing the flow rate caused an increased crystallinity of silk extruded through the feed needle. In the semi-batch system, droplets showed circulatory flow during freefall. At all feed heights, mixing of silk molecules within free-falling droplets was driven mainly by convection due to the high fluid velocities. Consequently, the impact of non-uniform silk concentration across the droplet on the solvent-anti-solvent mixing efficiency could be neglected. However, for flow rates of high shear, so such as from 1 to 16.96 mil per minute, self-assembly within the droplet could occur during flight due to the microscale diffusion length of the silk molecules. So the reduction in free water concentration from the droplet could have reduced the solvent-anti-solvent mixing efficiencies and provided a confounder. The impact of stirring and feed addition height was assessed at the 6 mil scale. The stirring rate showed simple effects for nanoparticle size, PDI, and yield. As the stirring rate increased, nanoassembly size and PDI decreased, while the yield increased and then decreased. As the feed addition height increased, nanoassembly size, PDI decreased, while yield and the zeta potential increased. Increasing the stirring rate and the addition height reduces the mixing time of the organic and aqueous phases, increasing the nucleation rate and resulting in smaller nanoassemblies with narrower size distribution and producing greater yield. Morphology changed from amorphous aggregates at the high mixing time conditions to more circular, less sharply edged, and less oblong nanoparticles as the mixing time was reduced. In bulk and micromixing processes at flow rates where the shear rate lay below the critical shear rate for silk, increasing the concentration of silk resulted in nanoassembly populations of lower size and lower polydispersity. In the stirred bulk system, at flow rates, as flow rates increased beyond the critical shear rate, the increase in assembly size and PDI occurred due to increased rates of shear-induced assembly. Conversely, without stirring, the reduction to mixing time, which occurred with increased flow rate, dominated over shear effects and caused reductions to the assembly size and the polydispersity index for 0.5 and 2% silk precursors. Similarly, the mixing time was the dominant factor controlling self-assembly in the micromixer, with faster nucleation at higher flow rates, resulting in smaller nanoassemblies with narrower polydispersity. In bulk mixing conditions of low mixing time, shear-induced assembly increased as the flow rate increased and the critical shear rate was surpassed. This resulted in polydispersed mixtures of lamellar, nanofiber, and nanoparticle assemblies for all silk precursors, and nanoassembly size is increasing for the 2% silk precursors. The roundness of nanoassemblies increased and the aspect ratio decreased with higher flow rates for the 0.5% silk precursors, while the roundness decreased for 3% precursors. At flow rates where the shear rate lay below the critical shear rate for silk, increasing the concentration of silk precursor resulted in particle populations which were more circular, less sharply edged, and less oblong. In micro-mixing conditions, amorphous aggregates were formed at flow rates where the critical shear rate was not exceeded. Increasing the flow rate resulted in more circular, rounder, and less oblong nanoassemblies at the 0.5 and 3% silk precursor concentrations, and caused size reductions across all silk precursor concentrations. Morphology could be tuned from rod-like narrow polydispersity assemblies to spherical narrow polydispersity assemblies by increasing the silk precursor concentration from 0.5 to 3% in the high shear micromixing processes. In conclusion, a semi-automated, semi-batch system and a staggered herringbone micromixer were characterized and utilized for silk nanoprecipitation. In the semi-batch system, increasing feed addition height and stirring rate reduced the organic aqueous mixing time. Reducing the mixing time shortened the growth phase of silk self-assembly and resulted in a shift from amorphous aggregates to spherical particles. The silk self-assembly was then further optimized for morphology control by increasing shear processing and varying the silk precursor concentration. In bulk mixing, nanofiber and lamellar assemblies were formed as mixtures with spherical particles. Due to the sufficiently low mixing time provided by the micromixer, however, the silk precursor concentration could be used as a controllable input factor for the formation of monodisperse, rod-like, and spherical nanoassemblies, which are suitable for use as nanomedicines. I'd like to thank the SEEP and the PERI groups and the other collaborators involved with this project. Thank you for listening.
Thanks for answering all these questions, giving the presentation, having time for us, and thanks to the audience for coming today. And yeah, see you in 4 weeks' time, and goodbye.
Thank you very much.